Good afternoon, everyone. I hope you are doing all right and ready to learn some physics. So, we started talking about magnetic force and magnetic field last week, and we are continuing on the same thing this week as well. So, last class we learned that when there is moving charge on a magnetic field, it experiences force, and current is also basically moving charge. So because of that, if there is a wire or conductor carrying current that's moving in a magnetic field, it experiences force. So the conductor experiences force because the charges experience force. So here, and then we also talked about like how the separation of charge can occur when the charges are moving in a magnetic field, and that can develop electric field. So today we're going to be focusing on or developing on that idea, and then going to be learning about how we can generate EMF or current by making conductors move in a magnetic field. Okay, so that's how the electricities are generated that we use in our daily life. So it's generated from moving conductors. So the generators have coil made up of conductors, and it spins in the magnetic field, and that's what gives us electricity. Okay, so now to look at the basic principle of that, first, rather than talking in terms of coil, let's just talk in terms of the conductor, straight conductor. Okay, so here, this one is a conductor, and since it is a conductor, it has both positive and negative charges, and that's what I'm trying to show it by, you know, drawing those charges over there. And there is a magnetic field, and this cross means magnetic field is into the phase. Okay, so now let's make this thing move. So let's suppose it enters moving with velocity v. So it's going to the right on the screen. So when it does, while it's doing it, what happens is the charges experience force. So let's think about what direction the positive charges would experience the force. So if we calculate the direction of forces on the positive charge, on the negative charge, it's going to be exactly opposite, right? So, so that means, so free up your right hand and space fingers and the thumb. And then now the field is going into, so I guess palm down is good. But line up these fingers in the direction of velocity, okay? So in this case, it's moving to the right. So when I crawl my finger to the field or into the page, what I find my thumb is, like it's basically pointing towards, upper part of the screen. So does your thumb points in that direction? Try that. Did you try that? Okay. So that means positive charges experience force in upward direction here. So that's for positive charge. And for negative charge, it's going to be that, right? It's going to be pointing down. So that means there's going to be a separation of charge like that. So the electrons gonna move on this side because they are experiencing forces. Of course, the positive charge, they also experience force. They cannot move. But since some of the electron left that, what happens? There is now more positive charge. So that's how the charges separate in a conductor, just like we have in a battery. Battery has a positive terminal and a negative terminal. So in that case, chemical reaction separates the charges. In this case, what happens is the force due to magnetic field on the charge separates the charges. So remember that force develops only when charge is moving. So that means the conductor has to be moving. So when conductor is not moving, what happens? No force. So there's going to be recombination of this. So that's why this conductor has to be moving all the time to get that separation of charges. In another word, to get the, let's say, EMF. So here, each of these charges are, experiencing forces. One force is force due to magnetic field, and that's what we said, okay, the negative charge experience in that direction. But now, since there is separation of charge, that means there is electric field as well, going from positive charge to negative charge. So the negative charge over here tries to move in that direction, means they are getting force in the direction opposite to the field. So that's why there are this balancing, two forces acting in opposite direction. So those forces depends on the velocity. So by adjusting the velocity, we can make them in equilibrium so that so the forces are in equilibrium, so charges remain stationary at that point. So in that situation, these two forces have same value in opposite directions. That's what I'm writing in this equation. So we know force, electric force on a charge Q due to field E is Q times E, right? So that's the force due to electric field. And this is the force due to magnetic field. In this case, sine theta, I'm not writing it because theta here, see the B is moving to the right and B is going into the page. So that means there is 90-degree angle between them. So sine 90 degree is 1, okay? So that's why I'm just writing these, okay? So that means this is electric force, this is magnetic force. And both of these forces are acting simultaneously. So these forces are also known as Lorentz force, okay? So there is a magnetic field, combination of magnetic field and, or I should say electric force and magnetic force in a moving charge is known as Lorentz force. So those forces is the sum of this QE and QBB, right? Depending on what direction they are acting. So total force is going to be something like that. Here, these two forces are in opposite direction. So that's why rather than being added, they are being subtracted. That way we can say, okay, they are equal, something like this. So we can cancel Q. When we do that, we are now left with this. So if we know what magnetic field is here, what's the value of the magnetic field, and how fast the conductor is moving, we can tell what is the electric field here. Okay. So now we want potential. We want to write in terms of potential difference. So there is a relationship between electric field and potential difference. Remember, we defined electric field as negative delta V over delta X. So this This is change in potential. And this is electric field. Negative sign simply tells us that about the direction in this case, because electric field is a vector quantity. Okay? So delta x is basically a separation distance between 2 points where we are calculating the delta V. Okay? So for example, this could be VI, this could be VF, and remember these are uppercase voltages. So that means they are potential, not the velocity. So there is velocity as well, which is written as lowercase. I have to be careful. So that's delta V that goes in here. So that means delta V. So let's forget about the direction here. The value gonna be E times delta x. So in this case, the separation between charges is at the end of this conductor. So that delta x is going to be same as the length here, this length of this conductor, whatever that is. Okay? So that means I can write the potential difference between 2 points on this conductor, endpoints, 2 endpoints in this conductor is electric field times the length of that conductor. So now we already found that electric field is V times B. So we can plug that in there. So that way we get this potential difference generated is equal to VBL. So it depends on length of the conductor and the magnetic field applied and how fast the conductor is moving. So that is the also known as induced EMF. So we induced the EMF here, or also called motional EMF. It came from the motion. It did not come from the battery, right? There is no battery here. So now it's acting like a battery. What is acting like a battery? Moving conductor. So that's why the name motional EMF. Okay? So that's how we generate the electricity, folks. So here is a question for you. So this being first question, I am giving you 2 minutes. So clockwise means going something like that, right? Clockwise. Counterclockwise. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So we mostly got counterclockwise, and there are some clockwise as well. So what's the difference between that one and this one? So same direction of magnetic field, but conductor is moving this way now, not that way, right? So that is the difference. So I guess that's gonna make a difference. So here it would be like this, because current starts from positive charge, means it's gonna be going counterclockwise in this case. But in this case, the velocity is this way. So that means, again, arm is down, but the finger has to be pointing in the direction of velocity. So when I crawl my fingers down in the direction to the magnetic field, what happens? The thumb is pointing towards me. I just noticed my microphone is far from me. I don't know how well you are listening. Okay, so that means the positive charge is going to be this side and negative charge is going to be that side, means current going to be flowing. Oh, let's see, did I get that right? So that way, and positive charge, so that means yes, negative going to be there, positive going to be there. So that means current going to be flowing that way. So is that clockwise or counterclockwise? Oh, that is clockwise. Turned out to be a little difficult question. Anything you like to add or ask, folks, here? Since many of you made mistake. Okay, so I don't see any question. I don't hear anything, so I'm gonna move on. So here is problem. So we learned that EMF developed gonna be VBL. Okay, so that's gonna be the EMF developed here. So current gonna flow in that direction. So if the resistance here is R, and then what is the value of current? So using Ohm's law, so there is only one source of EMF, and this is series circuit. So this is like, this kind of circuit. I think I drew other way around battery. So this is like this kind of battery that has a EMF that and resistance R, and EMF is VBL. Okay. So using Ohm's law, so that means we can, since there is one source and one resistor, so VBL, so Ohm's law, so current is voltage over resistance. In this case, potential difference is EMF over R. So EMF is VBL over R. So that's how much current going to be flowing in the loop. So I see there is a question on the chat. So how does the thumb pointing towards us indicate that it is clockwise? So towards you, I think, was that clockwise or counterclockwise? Did I say that incorrect on the previous? So in this particular thing, thumb is pointing towards me. Okay. So that's why this side has a positive charge and negative charge. And we know current starts from positive charge terminal and goes to negative terminal. So that's why it is clockwise. Okay. So now if thumb was pointing towards camera, that means on the upper side of the screen. Okay. So there is a screen, camera that way. So when I look at the screen, this is my upper side of the screen. Okay. So that means there is positive charge over here. If finger is pointing towards you, and then negative charge is this, just like we had here in the previous slide. Okay. So did we have, yes. So in that case, what happens? The thumb is pointing towards you, means on the screen it is on the upper side, positive charge. So when I draw, let's say if I were to draw current here, so since there is no circuit, current doesn't flow here. So, but if there was this complete circuit, just like we have on the previous slide, then it's gonna flow like that, and this is gonna be counterclockwise. Okay. So I don't know if I said otherwise last time. But this is how it works. Okay. So this is exactly opposite because B is still same, but the B reversed. And because of that, I had to turn the palm on the other direction. So my thumb is now pointing down in the screen. Okay. So do you guys want to practice? Bring your, four fingers, line up in the direction of V, and palm, keep the palm down so that you can crawl down because field is coming. Field is going into the page. Cross means into the page. Okay. So here we change the direction of V from the previous slide. Now let's say if the field was coming up rather than cross, if they were dot like this, that means field is coming up. So in that case, yeah, V is still that, but now I have to keep my palm up so that I can crawl in the direction of field. Okay. So in that case, now this one goes that way. So it depends on what direction B is, what direction B is. And then our skill of orienting our hand, right hand, in correct direction. So those are the things you need to keep in your mind. Okay. Okay, so that is the current. So induced EMF divided by the resistance of the circuit. So now here is, I'm putting a light bulb here. So same thing here, right? Same circuit. Here this was connected and I said there was resistance. Now I am showing, okay, that resistance is actually light bulb. Okay. So that means this light bulb gonna light up as long as it's moving. Okay. The conductor is moving. And there is enough potential difference to light it up, of course, if there is. So we can estimate, like how much power we can generate by just making this thing move. Okay. So if the bulb has coil resistance R, what is the power dissipated in the bulb, right? So we already learned that, from previous question, I is V B R, sorry, not R, L over R. So that's what we learned. And that means the power that dissipates in a resistance. So if we know resistance and if we know current, then we can write power as I squared times R. Remember, power can be written three different ways: I times V squared times R. So this is basic definition. And we can do, use Ohm's law and write like that. Or we can write something like that. Power can be written three different ways depending on what we know. So we can, the power dissipated, usually we like to write in terms of current and resistance, but same thing you're going to get even if you write this. So in this case, this equation is not suitable because the resistance is given and this equation does not have resistance in it. Okay, so we can use either this or this one. Okay, so that means it's going to be B, B, L, and since this is I, it has to be squared. So that means this has to be squared, this has to be squared, this has to be squared, and that has to be squared. Okay. And then there is R. So this R cancels. And actually, if I had used this one right there, would have been just this in one step. Or probably it would also take two steps. So power is B square L square divided by R. Okay, so that's what we get. So now, so it looks like I have a text over there in the slide. So let me write this result we have over here. So this is power. Okay. So how fast the rod has to move if we want to light 5-watt light bulb? See, usually we use 60 watt. If it is LED, we may get away using 20 watt or something like that. Usually this 5-watt light bulb is like a one we use as a night light. Okay. Sometimes it's also called 0-watt bulb, but of course they're not going to be 0 watt. So usually it's 5 watt. So even for that, even if we want to just light that tiny, light bulb, how fast it has to be moving. Let's just, estimate that. So that gives us, like why this is not the method to use to generate electricity. Okay. So now it says power is 5 watt. And then length is 1 meter. Oh, those things are already there. So I think I don't need to list them again. So length is 1 meter, resistance is 1 ohm, and B is that. So we are looking for V. So by using this equation here, see, using P is V square, B square, L square over R. So we have everything but V, right? So power is given, and then B is given, L is given, and R is given. So only unknown is V. So we should be able to calculate V from here. So by rearranging this equation, what do we get for V? So let's say V square going to be P times R over B square times L square. Okay. So I'm just rearranging this. So R goes here on the top, and these two comes down here on the bottom. Okay. So that means we know everything. Oh, now what is V then? V is PR over B square L square under the square root, means 5 times 100 times 0.01 squared. Ooh. And by the way, that is 10 to the power negative 2 squared. We can say that. Okay. That way it's easier, I think. And L is 1 meter. Okay, that is good. 1 square is just 1. So we have 10 to the power negative 4 in the denominator, means we have 500, and then when this comes up, it becomes positive 4. So this is like a 10 to the power 6 meter per second. So like it's a million meter per second. That's very impractical. Okay, so that's why we don't use this method to generate this. So nothing can move this fast except light, okay, and some electrons. Other than that, no object, material, can move that fast. So this is not a practical method of generating electricity. But this gives us basic principle, okay? So now it's asking us what is the magnetic force on the moving rod, right? See, we have to keep on applying force to keep this speed, and because there's going to be a drag force acting on this. Otherwise, you set up the motion and forget, and you keep getting the electricity, right? So it doesn't happen. So there's going to be magnetic force that, opposes the motion of this thingy. So we learned that magnetic force due to magnetic field in a wire is, let's see, what was that equation? I L B sine theta, where theta is 90 degree in this case. So that means it is just I L B, and we know I, we know L, we know B, means we can calculate force. Okay. So we learn basic principle of charge separation, and that's what gives us the EMF. And that's the idea used. But rather than making a rod or conductor move in a rail and generate electricity, what we do is we do this. Okay, we make a coil and we spin the coil. Okay, so we just learned that EMF induced. So let's say we make a coil. So one part of the coil is like a wire, right? One wire, just like we saw. So we can say, okay, that field EMF in one side is this much, and now EMF from the other side gonna be same amount because magnetic field is same, B is same, L is same. Okay, so now this V, what is this V? So in this case, it is linear, the V came from the linear motion, but in this case, it's rotating. But we know from circular motion, these two things are related. So for example, we can say, okay, rather than, moving with speed V, we can say it is spinning with angular speed omega, okay? So just like V is displacement over time interval, omega is angular displacement over time interval. So we learned this in physics 1. So now we are using that idea over here. So that means theta gonna be just omega times t, okay? So delta theta can be thought as a theta only if we say theta I or initial is 0, then final minus 0 is just final, whatever that is, we can say just theta, okay? So theta can be written something like this. And then we also learned that V is same as R times omega. So that comes from circular motion or rotational motion. In both cases, we talked about these equations, okay? It is in physics 1 equation sheet if you are interested. Okay, so now including theta as omega times t and B as R times omega, now this equation now gonna work for the things that's spinning, okay? And that's what we are doing, okay? So here there is R and there is L. So what is R? R here is radius, okay? So for example, in this case, when it is spinning, we can think of, you know, let's say R is something like that. And we already know L is length of this, okay? So, so that means if I want, like let's say this from both of these, so this is gonna double. So that's why I'm doubling it. Now it makes this 2R, see this 2R becomes now whole width of this and length. So we are multiplying width and length. Where is length? Right here. So when we multiply width and length, what do we get? We get area. So that's why I'm replacing that by area. So that way, once I have area, the coil does not have to be perfectly rectangular. It can be circular or in between, right? So that's what, that's how the coil are usually, they are circular there. So if circular, then it's going to be that area, okay? Area of the circle. So when it is, circular, then area going to be I times R squared. So now what's happening is this, when it is spinning, then its value goes from some maximum value. And when theta is 0, when this angle is 0, then sine 90 is 0. So EMF goes from 0 to maximum and then negative. So that's why we get this kind of oscillating or alternating current. And we talked about alternating current when we talked about currents, right? So basically that's how we generate the alternating current. So the maximum value or peak value is equal to this product of these three things. Okay, so that's what I'm writing here. So I max, or sorry, EMF max. Sometimes we may write something like that. Sometimes we may write something like just M, okay, rather than writing max all the way. Or sometimes you may also see written something like this for the maximum value, okay? So same notation. So this notation is for the product of these three things, okay? So that's what that is. So that's how we generate really, okay? So if we go to the hydroelectric power plant, what do we see? We see these cylinders. So these cylinders house the, motors like this, or let's say the coil like this, right? And there is magnet and coil in each of those, right? So what has to happen? The coil has to be spinning, right? And so if coil is not spinning, electricity not going to generate. So to spin the coil, you can use different ways. Of course, you can put the handle and crank it right with the hand. Not going to be very practical. It's not going to generate enough. And by the way, this number of turn going to increase the value. So did I write that N thing here? So this is from one coil. but this generator, they have like thousands of them. So we need to multiply that by n to include the number of turns, okay? So in this case, if it is hydroelectric plant, what happens? So you have this fan kind of thing connected on the head, okay, over there. And then when water flows through that, it makes that fan spin. So that means when fan is spinning, the coil is also spinning with the same rate because fan is connected to the coil. And the magnets are there, right there all the time. And this coil is spinning in between the magnet. Okay, so that's how it's generated. So probably, you may have seen or used this dynamo in the bicycle. So basically it has the similar structure. See over here, there is this head that touches this tire. So when tire is rolling, what happens? This thing spins, and that makes this connected coil to spin, and that's how electricity is generated. Of course, there is also magnet here. Okay, so it shows a magnet here and magnet there. Okay, and then there is coil somewhere spinning. Okay, so that's what happens. So faster you go, more you generate. Okay, so now in this question, let's see what is it asking. Suppose a bicycle generator has 150 tons of wire in a circular coil of radius 2 meters. So total number of tons is n, let's say, is 150. And then coil radius r is 2.0 centimeter. So let's convert that into meters. 2.0 times 10 to the power negative 2 meters. We need to divide by 100. So dividing by 100 is like saying 10 to the power negative 2. Okay. What should be the minimum rotational speed in RPM, revolution per minute or rotation per minute, right? So that means we want omega. But our omega in our formula gonna give, formula gives in SI unit, that means radian per second. So we need to convert that to revolution per minute, okay? So we want EMF to be 3 volt. So see how this thing, EMF, generated EMF goes from 0 to maximum to that. So it says amplitude. So that means that's the maximum value actually, okay? 3 volt. And then magnetic field, 0.1 Tesla. And we are asked to find, yeah. So we learned that. So for the maximum value, so when we get maximum, we get maximum value when theta is 90 degree or sine theta is 1. Okay, so that we know. So that means we can write that formula we had. Do I remember that? N times omega B A. I think that's what the formula was. Okay, so that is that. We want omega. So let's solve for omega. Okay, so that means we know everything. So we should be able to get the number here is going to be in radian per second. So now how do we get RPM? So there are 2 pi radian in each revolution. So that means that's going to be 1 revolution is 2 pi radian. And then times, see, it's RPM means minute. This is second. So we need to get rid of that second. So there are 60 seconds in 1 minute. Okay, let's try min for minute. M may look like meter. So that's how you convert it. So that means the radian here cancels with radian here, and the second here cancels with second. So you have revolution on the top and minute in the bottom. So whatever number you get, you need to multiply that by 60 and divide that by 2 pi. And pi is 3.14. You can use that. Okay. So that's how we solve problem like this. Okay, so that's the electric generation. So now, rather than, like, let's see, there are other ways we can generate EMF. So Faraday was playing with the circuit and switch and so on, and discovered something, okay? And if you are taking physics 2 lab this semester, probably you will watch this video. So those labs I put together and those video I put together, hopefully they are using it. But I did not make this video. I got this from YouTube here. Okay. So let's try playing this. So what we have is there is this meter. See how it's written A over there. So that means it means ampere. So that means it's detecting current. Okay. And there is a loop, just like the loop that goes in generator, right? So you have this long wire, made in a loop. And this has less number of turns. This one has larger number of turns. And there are some connecting wires, okay? So that you can see if there is any current flowing through this wire, okay? So in this case, we're not connecting any battery here, okay? So in the generation, electric generation, what we did was we put the magnetic field and we make the coil move, but it does not have to be coil moving. It can be just magnet moving, coil just sitting there, or both of them can be moving, gives us the current or induced EMF. Remember, once we have induced EMF and there is some sort of loop, that means we can measure current rather than EMF. Okay, so that's why often we call it induced EMF rather than, induced current. We talk in terms of induced current rather than EMF. Okay, so that's how it is. Let's watch this video now.
Current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil.
And by the way, let's see, going back a little bit. So a couple of things I like to point out when we are watching this YouTube video, kind of sometimes things could be a little bit misleading. Video, there is nothing wrong with the video, but sometimes explanation could be a little bit, So it says positive current and negative current. So rather than saying, like saying, okay, positive and negative current, we may want to say, okay, it's going this way or that way. Okay. So in this case, I think what this person means is that this needle deflects to the left. That means negative current. And when it deflects to the right, that means positive current. That's what this person means here. Okay. So here, there are these number of turns, not that big. So if you can, pay attention to the needle, see how much it deflects, okay, how far it goes when this person pulls the, put the magnet and pulls, right? And also notice when the needle actually moves, okay? When magnet is going in and coming out, is there current there when magnet is all the way in but not moving, right? So can we pay attention and watch those kind of thing here? I'm going back, let's see.
Changing going into the coil, there's a positive current.
Oh, I am messing thing up.
Magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flow.
So there is deflection only when magnet is either it's going in or coming out. When magnet was held steady over there, not moving, when magnet was not moving, needle wasn't deflecting. Did you see that? Let's watch one more time.
Going into the coil, there's a positive current.
See, it's not
When
deflecting
it's
anymore
changing,
when
coming
magnet
out of
is
the
not
coil,
moving.
there's a negative current flow.
Okay.
And now let me connect the 100 loop coil. And I'll start by moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. If I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also.
Okay. So this was first discovered by Friday. So what did we notice here from watching the video is that it's not just the magnetic field, okay? So it depends on number of turn and how quickly magnet is moving. So to combine that idea of the, what's the, let's say, uh, structure of the coil is or the area of the coil is and the magnetic field and how it's changing and so on, rather than talking in terms of just plain magnetic field, sometimes it's a good idea to talk in terms of flux. So whenever we have field, we can define flux corresponding to that quantities, okay? So we had electric field and we can have electric flux, okay? Similarly, when we have magnetic field, we have magnetic flux. So what is it? So it's like, just like we use that in daily life, sometimes on campus, right? On a game day, for example, or Sunday. Usually game day is Sunday. Sometimes it could be Thursday. So sometimes we see a lot of people moving around, right? So when game is over, what happens? A lot of people come out of that door. So we say, okay, flux is large. There is large number of people passing through that door, means flux is larger. But if there are only one or two people passing, flux is not so large, very small. And if there is no person passing through that door, that means flux is zero. Same idea here. So for a given area, like a door, if there are, let's say in this case, we see three of these passing through that area right now. Okay. Now, if I were to draw more and let's say they were going something like that, then we say flux is larger. So so this, when these lines are closer, that means we say, okay, strength of magnetic field is larger. Okay. So flux depends on the strength of the magnetic field and also the orientation of this coil. So for example, if door is in a normal situation like this, then person can get in, get out through the door or pass through the door just fine. But if door is fallen flat, then person cannot pass through the door. That means flux becomes zero. So orientation of the door also matters. So same thing goes here, orientation of the coil also matters. Okay. So we define flux as the product of magnetic field times the area of the coil, strength of the magnetic field times strength of the area of the coil times the cosine of angle between them. So now angle between them means, see, magnetic field, yeah, we know this is vector, so it's easy to tell what direction it is, right? Usually, it's given. But how about the area? So there is this loop sitting there. What's the area, right? So we cannot tell the direction of area of a loop unless there is a current flowing, okay? So that's why you see I am showing this current flowing here in the loop. So now, if current is flowing in the loop, then what you can do is you can crawl your finger, you can grab that loop. Do I have some kind of loop here? Okay, so you can grab the loop in the direction of flow of current. So if current is circulating like that, you grab like this, and now thumb is pointing up. If the current is going all the way around, then you need to do this, and now you see it's pointing down. So the N or the normal you see here is the direction of the area, okay? So whether it's pointing up or down gonna depend on which way current is circulating. Right now it's circulating something like this. So when viewed from the top, it is going something like that, means it's counterclockwise, okay? But if it was going clockwise, let's say like this, then this normal would be pointing something like this. So the theta is angle between that normal and the B, okay? See, this is now cosine. We had sine for the force, right? In the equation, we had sine theta for the force. Now for the flux, we have cosine, okay? Flux is a scalar quantity, turns out, okay? So now with that, this is how we define the flux, okay? And I think I have written here what I just said. So now the unit of the flux gonna be unit of this B and A, cosine theta, they don't have unit. So B is magnetic field strength, means it has unit Tesla. The area means meter squared. And this Tesla times meter squared is also known as Weber. Okay. Again, name of scientist. Okay. So based on this equation, so what happens is EMF induces when flux is changing. If flux is not changing, EMF does not induce. So when does the flux changes? Understanding that is important to know whether there's going to be any kind of induction or not. So it depends on three things. So if you change B, flux is going to change. If you change A, so let's say right now the coil area is this, now suddenly you have this big area, right? You use bigger radius coil, then now the area is different suddenly. If you go from smaller loop to the, larger loop. And the angle, so orientation of that loop, right, with respect to magnetic field. So all these three changes the flux, okay? So now here is a question for you about just what we talked about. So to calculate flux, we have to use correct angle. So because of that, let's do practice of actually learning that. And you have a minute total. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So we have kind of A and B together, okay? I mean, about the same. And we also have C and D, okay? So here is our area thingy, okay? So in this case, what happens? Angle is always the angle between normal and the B. So that means it's theta, 1, okay? So this is the angle we should be using in this formula to calculate that, not this angle, okay? A is correct answer. We saw that right here. See, the angle is angle between normal and the B. Okay, so that's what that was. Okay, so it looks like it's a good time to take a break. So let's take a break, and after break, we're gonna pull on this one. Okay, folks, welcome back. So here is a question for you. So we are changing two things. One is magnetic field strength. Another one, area, by changing the sides. And making something like that. So anyway, so I'm opening the poll, and you have 1 minute and 30 seconds to poll on this. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. So we're getting all of them, basically. So flux is given by, so here, what's not changing is this cosine theta. Okay, we're not tilting the wire or anything like that. Whatever it was, we are just keeping like that. So we are changing B, and B goes to half of that. And we are changing length. We're doubling length. Square loop area means L is square. So when L goes to 2 times L, then what happens? L square goes to 4 times L square. So we pick up that factor of 4 over there in the area. Okay? So it increases 4 times because of the doubling area, but since we are, making this field strength half, there is this factor half over there. So half times 4 is 2. So that means, looks like it's up by 2. Okay, anything you'd like to add or ask here, folks? Okay, then moving on. So Faraday, we already watched video, but to discover that effect, Faraday used something like this kind of setting. See, there is a tiny compass there. So there is one coil and there is another coil. They are connected by this iron ring over there. Okay. So one of the coil here is like a solenoid, right? So when current passes through the solenoid, did we learn this equation? I think we did. Okay. So when current passes through this, so in this case, number density of the turn, so that is fixed for a given coil. So that means it just depends on current. Larger the current, larger is going to be the field. So depending on how much resistance is there, we can tell how much current going to flow, EMF over R, right? We know that. But when switch is off, there is no current flowing, so current is 0. Now you close the switch, turn on the switch, and then what happens? Suddenly current goes from 0 to that I value, whatever that is. See, there is change, current changed, went from 0 to that value. So that means when that current is changing, when no current flowing, field is 0. Now there is maximum current, let's say, possible for the circuit. Then there is that field. So that means field went from 0 to B also went from 0 to some value there. Okay, let's say B max. Okay, just like it went I max. So field is changing here. That means flux is changing. So when does it change? When current goes from 0 to the maximum value. And it happens in a very short time interval, okay? You connect and there is current. And once current is not changing, what happens? Flux is not changing. So that means even when this switch is on, what happens? The current is flowing, good, but it's not changing, means flux is not changing. So we don't see any kind of effect over there. But the moment you turn on the switch or off the switch, that very short time interval, for that short time interval, what happens? You see this magnetic needle kind of compass shows there is this magnetic field, okay? So this flux that generates here gets coupled to this coil. And then what happens is that's going to induce current here. And because of that, it feels the magnetic force, okay? So this is a magnet, and this coil also becomes like electromagnet, and because of that, what happens? It deflects. But that happens only when the switch is, you know, either turning on, or the moment is turning on, or the moment is turning off, okay? So it is not all the time. So that's why I'm highlighting this one here, okay? So just like I was saying, so in this coil, when current is passing, there is this flux passing through that. Okay, we can talk in terms of field or flux. Okay, so switch off, no field. Switch on, there is field. So it goes from no field to field. So the field changed means flux changed. Okay, and then over here, what happens is now this one has now this magnetic flux or field, okay? And that's what it is detected. So this is the Faraday's discovery. And how much EMF is induced by this kind of situation is given by this equation here. This negative sign simply means direction. So the actual equation is a rate of change of flux. So it's not flux, it's the rate of change of flux. So if flux is not changing, no EMF there. Okay, so we have to be very careful about it. So negative sign simply says that, okay, it opposes the change. We'll talk about that. That's what the Lenz law is about. Okay, so flux is given by that equation, and negative sign simply says that the induced EMF opposes the rate of change of flux, just like I was saying. Okay, so flux, when does the flux change? When B changes, or A changes, or theta changes, or more than one combination, okay, change. Something has to be changing for the flux to change. And EMF is induced only when flux is changing. If it's not changing, so it's not. So if we have this, if current is not changing in the circuit, that means no induced EMF. Okay. So here is one problem related to that. So here I just copied those relevant formula. So in this case, it says, what is the induced current in a coil of radius that many centimeter? So radius is given 4.0 centimeter. So let's convert that to the meters. So we need to divide by 100 or multiply by this 10 to the power negative 2, okay, meters. And here magnetic field is changing. So what is changing? Magnetic field. So I'm writing that. So it is going, so B final minus B initial. Final is 0.5 Tesla and initial is 0 Tesla, means it is 0.5 Tesla. So here flux is changing because magnetic field is changing. Assume that the resistance of the coil is that. So if we want current, then we have to have resistance. So lowercase r is for radius and uppercase R is for resistance. Okay, the different notation. And it says field is perpendicular to the plane of the coil. So plane of the coil is this, field is this, and so that means normal to the field also going to be that, means theta is 0 here. Okay, so perpendicular, we may be tempted to use 90 degree, but perpendicular to the plane, but angle we measure is from the normal, so that's why theta has to be 0 in this case. So that makes cosine 0 is 1, positive 1. Okay, so that means theta is 0. So now it's asking us to find what is the induced current. So we know induced current is induced EMF over resistance. So induced EMF using Faraday's law, which is this equation basically. So this means magnetic flux, change in magnetic flux. So we can ignore negative sign if we like. It's not asking us to find, which way current is circulating. So the value of this is going to be just this thing here. So delta and phi is this here, BA cosine theta, okay, over time. Neglected the sign or direction, only computing the value. Okay. So now here, see how we can handle what is changing. So with time, in this case, what is changing with time? B is changing. Is area changing with time? It's not. So that means it's not changing with time, means we can pull that out from that delta thingy change. See, it's not changing. So that means we can pull that out. And then similarly, cosine theta, the theta is also not changing, means we can pull that out. So only thing that's changing is just this magnetic field. So we can write like that. And since theta is 0, this is basically 1. So that means we can write, okay, this is A times delta B over delta T. Oh, delta T is given, that I did not write it. Okay, so time interval 0.2 milliseconds. That means 0.2 10 to the power negative 3 seconds, or 2.0 times 10 to the power negative 4 seconds. So A is there, and delta B means, see, this is 0.5 Tesla. So maybe we should start plugging in numbers here. So area, so in this case, it says current in a coil of radius that much. So that means it is circular. So we can say, okay, area is pi r square, and cosine theta is just 1. And then let's write delta B over delta T. So now let's plug in everything. Pi, or 3.14, and then r squared means that 4 times 0, 4.0 times 10 to the power negative 2. This whole thing has to be squared. So we just wrote the area. Now we need to move on to this one here, right? So delta B is 0.5 Tesla. And then down here, that is this many seconds. So 2.0 times 10 to the power negative 4, okay, seconds here. So we see here, when we square 10 to the power negative 2, it becomes 10 to the power negative 4. So that means that the square thingy and this thingy cancels with this one here. 10 to the power negative 4 on the top, 10 to the power negative 4 on the bottom. And this 4 has to be squared. So 3.14 times 4.0 squared times 0.5. So that's all in the numerator. And in the denominator, it is 2. Okay. So the unit of EMF is voltage. So we can write that as a volt. 16, 8, 4, 12, 12.5, something like that. Okay. So 2 sig fig problem. So it's going to be either 12 or 13 volt. Okay, anything you like to ask or add here, folks? Okay, then let's move on. So now let's take care of, or let's learn how to take care of that negative sign. Okay. So that negative sign, or the Lenz law, says that when there is induced current in the coil, for example, like this, it always induces in a direction so that it opposes the change. See, negative sign means opposition, right? So it opposes the change, okay? Opposes the changing flux. So what is changing here? Flux is changing, so it opposes the change in flux. So that's what the Lenz law is. So now, to properly do it, we have to go through 4 steps, okay? So if you're just using one step, most likely you're not doing it correctly, okay? So all those 4 steps involved, I have drawn all of them in just one diagram. I added everything there so that we can see it here, okay? One page. So let's look at the step 1. Identify. See, we need to know what direction flux is changing. And okay, so we need to know direction of flux and how it's changing. Is it increasing or decreasing? Okay. So that means to know the direction of flux, we need to know the direction of field. Okay. So if we have a magnet, then we learn that magnet has this magnetic field going out from north pole. So that's why the purple thing here, I'm saying, okay, that's step 1. So let's say in this particular picture, it is to the right. Okay, right on the screen. Now, so now we want to see if field is increasing or decreasing where the coil is. So coil is here. So is the field increasing or decreasing? So in this case, magnet is moving towards the coil. Okay, magnet is moving towards the coil. So it's getting closer, right? It's coming closer. So if you bring magnet closer, what happens? Magnetic field becomes larger. Therefore, B is increasing. Which B? So there are 2 B's. See, one is this our good old B, and then another going to be B induced. Okay, we're not talking about B induced yet. We are still talking about step 2. Step 2 is shown in green here. So here, this tells us magnet is moving in this direction. This arrows means it's going closer. Okay, that's all we need. Closer the magnet is, stronger the field is. Okay, so that's step 2. Not that bad, right? Now, determine the direction of the induced magnetic field using the fact that induced will always oppose the increase or decrease. Okay, so this is the crucial. 3rd and 4th are the main steps here. Okay, 1 and 2, you just look at the magnet and which way it's going. You can tell that easily. 3 and 4, we have to think a little bit more. Okay, so now we need to figure out which way this induced field gonna be. So in this case, it's gonna either in this direction or in that direction. Okay, so which direction? So here, what's happening? It's increasing. How do you oppose when something is increasing? Okay, opposite of increase is decrease, of course. So how do you try to make it not, not let it increase, right? So if the fire is on the progress, you put the water in it, right? So here it's like, okay, this fire, this field is coming. So now you need to neutralize it. It's increasing, increasing. To oppose that, what happens? Now you need to develop field exactly in opposite direction. So why in opposite direction? Because it's increasing. To oppose the increase, you have to line that up in opposite direction. So original field is, let's say, going to the right. So now the opposing field has to be to the left. So do you see that here? So that's what I'm drawing in step 3, okay? So this field here, this color, try to match all these colors. So all these things are the relevant for step number 3, okay? So now we know induced field gonna be in the opposite direction of the original field. So now, where the induced field is coming from? Induced field, electric field comes from by generating current here, circulating current. So we learned that when current is circulating in a wire, what happens? It generates a magnetic field. And how do we find the direction of that magnetic field? Okay, how do we do that? So let me write this step number 3 here. See how I'm, marking that. So that's how I suggest you do when you are trying to answer this kind of question, right? So in this case, it has to be on the left. Okay. B induced has to be on left. So now we want magnetic field to the left. So now if we were to use right hand rule for the current and the, like field, what we can do is we can say, okay, thumb is, let's start by pointing thumb in the direction of field we want, because that's what we know. From step 3, we know which direction the field has to be. Okay, so we now know it has to be on the left. So I start by pointing my thumb in that direction. And then now I'm trying to find current, right? So current is circulating in the coil. So it makes sense to crawl these fingers, right? So which direction these fingers gonna crawl when thumb is pointing this way? They are doing something like this, right? So that means here step 4 is figuring out what direction is the induced current is, and that's what we want. Okay, so in this case, when I wrap my fingers go something like this when I grab that coil, right? So that means, I mean, they have to go like that when thumb has to be pointing this way. Okay, so that means current is circulating that way. And then that is the direction of current. How about direction of EMF? So for example, if current was driven this way, the positive terminal of EMF must be this way and negative terminal that way, right? So if we need it, and then we can say, okay, the positive is going to be pointing this way in the direction of flow of current, right? We can say that. But often we just end up using that, okay? So thumb pointing, thumb in the direction of thumb to the left in this case, in this particular case, left. So fingers crawl. So when I look from left, this side of the coil, so depending on which side of the coil you are looking from, the clockwise and counterclockwise is going to be different. So when I look from this side, this is counterclockwise. Counterclockwise when looked from left. Okay, so these I just copied from our note. including this picture. Okay, it is there. So you can go and look anytime. And of course, this slide is also posted on Canvas. So you can find that there. So we need a little practice for this. So that's why I am bringing some question here. So this is near side of the coil, means, that side is far from us and this side is near. Otherwise, when we look something like that, could be confusing. So North Pole is still pointing this way, but now we are moving the coil away, sorry, moving the magnet away from the coil. Okay, so that's what we are doing here. So for this, what should be the direction? So you have 1 minute and 30 seconds. So I'm sure you like to practice, so go through all those 4 steps. Okay. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly counterclockwise. So let's see, was that counterclockwise over there? Yeah, and that was counterclockwise here. So you don't see any difference between this one and that one, folks? See, the B, it was going towards the coil. Now it's moving away from the coil. Okay, so how does that change? Let's take a look. Okay, so now B is still to the right, step 1. B to the right. Now step 2, is the flux here increasing or decreasing? So the magnet is moving away, means flux is decreasing. Now step 3, most important step, I think. So now, which way has to be the induced field? Be induced. To the right or left, right? So in this case, the field is in this direction and it is decreasing because magnet is moving away from the coil. Okay, so it's decreasing. That's what we said. So that means it opposes it. So it says, okay, don't decrease, don't decrease. I'm going to help. I'm going to help. So how do you help not to decrease? By inducing magnetic field in the same direction. So when you want to oppose, you induce in opposite direction. Here, when you oppose the increase, you induce in opposite direction. But when you oppose the decrease, then you need to line up in the same direction so that they, rather than canceling, add up. Okay, so we want B induced to the right, just like B was in the same direction now. Okay. So now to get that, which way it has to go? So you start thumb in the right and then crawl your finger with palm up, right? Otherwise, your finger, if you were to crawl down, your finger not going to go, this thumb not going to point that way. So thumb has to be pointing this way, right, means now it's going to crawl. Let's see, it's going to go that way, means that is clockwise, okay? Okay, so looks like we still have difficulty, need practice. So did you go through this step? Go ahead, go through this step. Take a few moments here. Okay. Free up your hand, free up your mind, and then go through these, okay? Can you come up with the same result? Okay, moving on. Here is another question. This time it's easy to see kind of loop. Loop is flat on the screen and field are getting into the field. And in this case, it says flux is increasing, okay? So how is flux increasing? Yeah, maybe a magnet is coming closer to it, okay? And it does not matter whether it's north pole coming or south pole coming. Field gonna increase as long as magnet is coming closer, okay? Which way increases? That's a different story. So for that, this step one, okay? So anyway, in this case, you already know the direction. Step one is already there, okay? So again, a minute and 30 seconds for you folks. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see how did we do here. So mostly counterclockwise. So here flux is increasing, flux changing means there gonna be induction. Okay, so this is not. So now it has to be, see, it's increasing. So to oppose that, the magnetic field has to be coming out of the screen. Which one? B induced. B induced has to be coming out there. Okay. So so you point the thumb up, assuming that the screen is flat on the table. That's how my tablet is. So that means it's gonna go. So my fingers are curling like this way. Okay, when I'm pointing thumb up out of the screen. So that is called counterclockwise. So yes, B is correct answer in this case. Okay. So here is another one. And this time, just a minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. We mostly got A. Is that the case? So in this case, see, the North Pole is pointing away. So that means field goes from this way and comes from that way. So if we think field inside the loop is going that way, okay? So that is the original magnetic field. Now, what's happening here? The magnet is moving away, means flux is decreasing. Why? Magnet is moving away. So now, so that means to oppose that decrease, it has to line up the induced in the same direction as the original. Okay, so now to get the field on that side, I'm doing finger like this. So my fingers, thumb is going to the right. So my fingers are kind of wrapping it from down there. So that means it's like going something like this. So B. Okay, it's 50. We have one more slide, but I'll pull on this one next class. Okay, so if you have question, feel free to ask me, or else I'll see you next class.